Okay, so welcome everyone. Today we're happy to have Daniel Tsodikovich from the Tel Aviv University, who will talk about a billiard analog of the Blaschke-Santalo inequality. So Daniel, you can begin.
Thank you for the opportunity to speak here. So I'll talk about an analog of a Blaschke-Santalo inequality in the billiard dynamical setting. So first I'll recall some notions that are necessary to define the Blaschke-Santalo inequality, and then I'll explain what analogous question or what facts about the Blaschke-Santalo inequality we will try to generalize to the billiard setting and what can I show. So let's recall what the dual of a convex body is. A dual of the convex body. And when I say convex body, I mean a convex compact set with non-empty interior. So given a convex body K in Rn and some point Z in Rn, the dual of K with respect to Z, which we'll denote like this, is the set of all points in Rn with the property that for all Y in K, the inner product of Y and X minus Z is the most one. Hopefully I didn't mix up where to subtract the Z. No, I subtracted. Yes, I did mix it up. And X and Y minus Z. Yes, okay, of course. All points in Rn with a property that X Y minus Z is the utmost one. And this is always, so this is called the dual of K with center Z. And this is always convex and closed, because it's the intersection of closed half planes, half spaces. And if Z is in the interior of K, then this is also a convex body. So if Z is in the interior of K, then the dual is also a convex body. And which will have a zero in its interior, and moreover, this operation is involutive. So if I take the dual of K and then take the dual of that with respect to the origin, then I will get the shift of K to the origin. Now, what does this operation look like? So the case that we will mostly need is the case where K is a two-dimensional polygon, or in fact, even a triangle. So if K is a triangle, and this is the point Z, so we take the unit ball centered at Z. And then we take the segments that connect Z with vertices of K, and we invert them with respect to this circle. So we get 1 point here, 1 point here, and 1 point here. And then we take perpendicular lines to these segments at those points. So we get 3 lines one like this, one like this, one like this. And these three lines determine the edges of a dual triangle. So what you see in brown is the dual k with respect to z. Okay, so here we all have right angles. This is if z is inside the triangle. If z is outside the triangle, then you will still get these three lines, but you will get, but you need to take the correct half planes, so you will get something unbounded. So, for example, you will still get something that is bounded by these three lines, and you will still get this, but now you will take the other side of the half plane, so you will get like this domain if z is outside of a triangle in one of those regions. So you get a triangle, but just an unbounded one. So this is the dual. And the one thing to notice, which will be helpful, is that these angles are acute, even though if these angles are obtuse, because in this quadrilateral, we have two right angles. So this angle is acute, even though if all of these angles are obtuse. So this is something that we will need a bit later. Okay, so this is the construction of a dual body, and this is how it looks like when K is a triangle. So what is the Blaschke-Santalo inequality all about? So in Blaschke-Santalo inequality, we define the volume product, sometimes called the Mahler volume, of a body K. So this is the product of the volume of K with the volume of a dual of K, but this obviously depends on the dual, so we try to minimize it over all bodies in over all points inside the body. So this is called the volume product of K. And this is a zero homogeneous quantity, so we can ask about when is it maximal or where is it minimal or things like that. And there are several things that are known about this. So first, there is the actual Blaschke-Santalo inequality, that the Mahler volume of any K attains its maximal for the volume of a ball, of a Euclidean ball, where B is a unit of a Euclidean ball. And this result is known as the Blaschke-Santalo inequality. One thing that is not really known, it's still open, is what about the other side? So what about the lower bound for this? So this is open, this is known as the Mahler conjecture. The conjecture is that it is minimized when K is basically cubed, but there are also other minimizers. But the general case is open. Some other things that are known is at which point this minimum is attained. So the infimum is the minimum. Volume. Is attained at a point Z for which the origin is the center of mass of the dual. So in particular, when K is, for example, centrally symmetric, then if you take the dual with respect to the center of symmetry, then the center of mass will be the origin. And so for centrally symmetric K, 0 is indeed the optimal point. And so for centrally symmetric K, we can just talk about the volume of the product of the volume of K with the volume of the dual of K, with the center of duality being the origin. And one more thing is that we know what are the maximizers of a volume product in the cases of polygons. So for polygons, with at most n vertices, the volume product is maximized for the regular polygons. Is maximized at the regular polygon, regular n-gon. So these are some well-known facts about the Mahler volume. So I don't really want to talk about the Mahler volume. I want to define another quantity which has the same spirit, but instead of volume, we will measure something else. We will measure the length of the shortest closed billiard trajectory in K. So let alpha K denote the length of the shortest closed billiard trajectory in K. So let me remind you that the billiard dynamical system is the following. We have some convex body K, and we have a particle moving in straight line inside of K. And when it hits the boundary, it reflects according to the law of geometric optics, that the angle of incidence is equal to the angle of return. So these two angles need to be equal. And it continues this way. This also makes sense in higher dimensions. So you take with a tangent hyperplane, and you require that angles will be equal, and in addition, that the incoming and outcoming ray, together with the normal to the hyperplane, will be collinear. So this makes sense also in higher dimensions. And well, first of all, why are there even closed billiard trajectories? So this is not really obvious. So if K has smooth boundary, then it's easy to show that it has closed billiard trajectories, because you can it will be a minimum of some function, and then it's easy to show that they exist. So if K has smooth boundary, closed orbits exist. Closed orbits exist. But if K doesn't have smooth boundary, then it's much more complicated. For example, we don't know if an arbitrary triangle has a closed billiard orbit. So it's not known if an obtuse triangle has closed billiard orbit. Yes, so this is not really known. So instead, what we do is we consider generalized billiard orbits. In which we allow the particle to pass through corners of a boundary. So now if our particle enters a corner in the boundary, so this is our triangle. So suppose you have an orbit that gets to the corner. So in the classical definition, this orbit can't continue because this is not a smooth point. But in the generalized definition, we want to find one tangent, one supporting hyperplane to K at this point. So for example, we take this hyperplane, and then we take, and then we make the same definition, that the angle of incidence is equal to the angle of return, or something like that. So the question is, so an orbit is a generalized billiard orbit if you can find at the non-smooth points supporting hyperplanes with respect to which it will have a billiard orbit. So the continuation is not unique, but given a trajectory, you can ask if it is a generalized billiard orbit or not. And if we make this definition, then obtuse triangles suddenly have very nice billiard orbits, which are just the altitudes. This is a generalized billiard orbit because it is perpendicular to the tangents at both endpoints. So this is a closed billiard orbit in an obtuse triangle. By the way, for acute triangles, there are the existence of closed billiard orbits are known for 200 years or so, and this is known due to Fagnano. If we have some acute triangle, then a billiard orbit is obtained by taking the three altitudes and you connect the three feet of these altitudes. So this is the right angle, this is the right angle, and this is the right angle. So this is the Fagnano orbit. This is well known and has some many expressions for it. We will need one expression for it. So one of the ways to compute it is the following. So if one of the altitudes has length h and goes from an angle theta, then in this case, alpha of k is 2h sine theta. This is the length of a Fagnano orbit. Oh, and by the way, in triangle, this is the only closed free trajectory. There can be longer closed trajectories, but this is the only closed, the only free trajectory of length free. So this is alpha of a triangle. What do we know about alpha k in general? And so let me recall some results. There is the result of Gomi that says that alpha of k is at least 4 times the in radius of k. And if K has constant width, and if K is centrally symmetric, then this is an equality. When radius of K is the maximal radius of a ball that is contained in K. Another result, which we will use a lot, is the result of Bezdek and Bezdek, that give an alternative characterization of alpha K. So Bezdek and Bezdek show that alpha of K is the minimum over M at most n plus 1, minimum of P inside the PMK, but I'll now explain what it is, of the length of P. So K is a body in Rn. PMK is the set of all configurations Q0 to or Q1 to Qm. These are like sequences of points in Rn that cannot be translated into the interior of K. And the length of such an object is just the sum of the distances. So if this is P, and L of P is the sum of the distances. So the length of closed polygonal line So what is the result of Bezdek and Bezdek? But alpha of K is the minimal perimeter length of a configuration of M points that cannot be translated into the interior of K. And you can take M to be at most n plus 1. So this is the result of Bezdek and Bezdek. In particular, in dimension 2, it means that the shortest billiard orbit can always be chosen to be either a 2 orbit or a 3 orbit. So we can always restrict ourselves to such orbits. And so this is the result of the Bezdek and Bezdek. Why are even people interested in the shortest billiard trajectories? So first of all, the lengths of the lengths of closed billiard trajectories are related to Dirichlet eigenvalues in this domain. There's some correspondence to that. And the second was a work of Arshen Avidan and Ostrover that relates the shortest billiard trajectory to symplectic capacities, and this was used to show something about that Summer conjecture in symplectic geometry is actually related to the Mahler conjecture that we mentioned. So these quantities are actually related to symplectic capacities. And some of these results also generalized to in a more general setting, which is also used for the symplectic picture that is related to this. So what we are going to define is the billiard product of K, which is defined similar to the volume product as the product of the shortest billiard trajectory in K and in its dual. So this is the billiard product of K. And we will mostly focus on the two-dimensional case. So usually n will be 2, but some things are also true for general dimension. And now here I wrote infimum over z in Rn and not a z in K as opposed to the volume product, because a priori it's not clear that you can restrict yourselves to K itself. because we can have so if z is not in the interior of K, then K of z is unbounded. But even unbounded domains can have finite billiard trajectories. For example, if you look at a strip. If you have an unbounded domain like a strip, then you still have a closed billiard trajectory, but goes like this. So then even if a dual is unbounded, you can still have closed billiard trajectories in it. So a priori, it's not clear that you can just restrict yourself to K, but in fact, it will be true. And we'll explain. So the questions that we will ask ourselves about beta of K are similar to those that are asked about the volume product. So the properties of beta K that I'd like to show you is that first of all, just like in the Santalo inequality, it is an upper bound is the billiard product of a ball, and this is 16. This is true in general dimension. A beta of a ball is 16 because alpha of the ball is 4 times its radius, because the shortest billiard trajectory is the diameter. So if the radius is 1, and you travel the diameter twice, so the shortest billiard trajectory is 4. And then in the dual, it is also 4, so the product is 16. So this is true in general dimension. And all maximizers must have a constant width. So the distance between any two parallel hyperplanes that contain K is the same. And in in dimension 2, in R2, the opposite is also true. If K has constant width, then beta K is 16. In the Santalo inequality, the only maximizers are affine images of balls, so balls and ellipsoids. Our quantity is not invariant under affine transformations, only orthogonal ones, but still every constant width domain is a maximizer. Now, the second question was whether there is a lower bound. But here it's easy to see that there is no lower bound. I mean, the lower bound is 0. So maybe let's write it like this. So the infimum of beta K over all K is 0, because one can just take very narrow rectangles, and then their duals will be very thin rectangles. And then the shortest billiard trajectory is the product of these two small things, and it will can approach 0 arbitrarily close. So there is no meaningful lower bound for the billiard product. And another thing that we can ask is what is the point which minimizes when which you have an infimum here. So in fact, we can show that the infimum of alpha of kz is attained when z is the midpoint of a diameter of k. So we find the segment of maximal length that is contained in K, its midpoint will attain the maximal. This is only in R2. I mean, I know this only for R2. Maybe it's also true in general, but I don't know. And then we can try to ask, but it will be more complicated, which we'll show later. What are the maximal of beta K, where K is a polygon with at most 10 vertices? So in the volume case, it was the regular polygon. In our case, I don't know what are what the maximizers are, but I know that regular polygons with even number of vertices are not them. So for example, a square is not the maximizer along quadrilaterals. I do know that regular triangle is the maximizer among triangles, but for polygons with even number of vertices, this will not be true, and we'll explain it. Okay, so these are the properties of a billiard product that we'll show. So now we'll begin discussing why some of these are true. So the main part is sort of identifying this part. If you know this, then knowing the rest is easier. So the claim is actually that the infimum of alpha kz, where z is in R2, is equal to 8 over the diameter of K with equality in K when Z is the midpoint of the diameter of K. So this is the heart of everything. And well, for the proof, we'll need several cases. So first of all, we rule out that Z is not in K. So we can restrict the infimum to be infimum in K. So what happens if Z is not in K? So and most of the, well, some of these proofs are just you draw a picture and you see what it holds. So if this is K and we have a point which is not in K, this is a point Z. So you can do the following thing. You can take two support lines to K that pass through Z. Close enough. And this gives you an inclusion between K and this sector. So here you have a sector. Let's denote this sector S. So we have inclusion K is contained in S. So then this gives you a reverse inclusion when passing through a dual. So passing to the dual is an operation that reverses inclusion. So the dual of S is contained in the dual of K. But since I take the dual of S with respect to the vertex of it, so this is also a sector. And now if we look at the dual picture, so we have here a KZ, and inside it we have this sector. And this shows that that the dual cannot have closed billiard orbits, because a sector can't have closed billiard orbits. So one way to show this, and this is the fact that we'll need in general, is that the work of Bezdek and Bezdek implies that alpha is monotone. So if you take a larger set, then if you take a body that contains K, then any configuration that cannot be translated into K cannot be translated into the interior of a larger body. So when you take the minimum over a smaller set, so Bezdek, the result of the Bezdeks gives us monotonicity, which is a very important property for us. So now, if we look on our case, then we have this family of triangles, of homothetic triangles, which are isosceles triangles with this apex angle. Then these triangles are all homothetic. So alpha of all of these triangles is linear with this distance. So all of these triangles, where the shortest billiard trajectory will have its length increases unboundedly, and all of these triangles are contained in KZ. So if KZ had a billiard orbit, then it would have to have length which is at least all of the lengths of billiard orbits inside these triangles, but this is unbounded, so it can't happen. And so we have here a family of triangles T with a parameter, I don't know, A. So we have that all of TA are contained in KZ. But this means that their alpha must be smaller than alpha of KZ, but this is unbounded, because this is linear with A. So then we have some problem. So this is why we can restrict the infimum to K. So now we have a simpler claim that the infimum for Z in K, we need to show this. So this is what we have now. And this is what we need to show now. We are in dimension 2, so we know that in the dual KZ, the shortest billiard orbit is either a 2 orbit or a 3 orbit. So alpha KZ is realized by either a 2 orbit or a 3 orbit. So when I say 2 orbit, I mean an orbit with 2 collisions, and 3 orbit is an orbit with 3 collisions. So the case of 2 orbits is easier. So first we can show this for 2 orbits. And here is a general correspondence. So if we have a 2 orbit in the dual of K, so suppose that this is K, we have here a point C. So that in the dual picture, the shortest billiard trajectory is a 2 orbit. If it's a 2 orbit, then it has to be perpendicular to the supporting hyperplanes at both points. So what this means is that we have an inclusion from K and a strip. So if we take these supporting lines, when we have this strip, we which contains the dual. We have an inclusion Kz is contained inside this strip. So now if we take a dual, then this will reverse the inclusion. So if we take the dual with respect to the origin, where this is the origin somewhere, or well, it should be somewhere here, I think. It doesn't really matter. Then this gives us a shift of k, and the dual of a strip is a segment. So not too difficult to see that this is contained in some segment. I need to reverse the inclusions. And it's not too difficult to see that if this strip, draw it properly. So if we have some strip here, where this is A and this is B, then when we pass to the dual, we'll have endpoints 1 over A and 1 over B. So the length of this segment is 1 over A minus 1 over B. And this means that if this strip, so if we know the width of a strip, we can say how long can be this interval. So in particular, the length of this segment is actually at most 4 over the width of a strip. In this case, it's actually equal because no, I don't know it's equal. 4 over the width of S. But if we have a length segment of contained inside K minus Z, then its length is at most the diameter. So we see that 4 over the width of S is at most the diameter of K. And this means that the width of S is at least 4 over the diameter of K, but the length of the billiard orbit is twice this width. So the conclusion is that alpha of Kz is twice the width, which is twice 4 over diameter of K. And we proved the inequality that we want in this case. Okay, so this is the case of a 2-orbit. By the way, it's also easy to see the sort of converse construction. But if we take the dual with respect to to a diameter, so if this is K, and we take a diameter, and we take the midpoint of this diameter to be Z, then by more or less the same reasoning, we'll have that Kz is contained in a strip of width 4 over the diameter. Because again, in the dual, this segment will become a strip. So if K contains this segment, its dual is contained inside the dual of a segment, which is a strip. And this means that alpha Kz is less than or equal to times the width of the strip times 2, so 8 over the diameter of K. So to recap, what we showed so far is that there exists some point where the dual has shortest billiard length at most, what we want to show. And we showed that for all z for which alpha kz is a 2 orbit, we have a reverse inequality. And so this is what we showed. So to finish and to prove this claim, we only need to show that this inequality, that the second inequality also holds when z is a point where alpha kz is a free orbit. And the proof relies on two reductions. So now the claim that we are left with is that if alpha kz is a free orbit, then alpha kz is at least state over the diameter. So we have a reduction if a claim holds when K is a triangle, then it holds for any K. So this is our first reduction. Well, let's explain that and then we'll say the second reduction. So again, the proof is mostly by pictures. So we have this K. Come on. We have K and we have some point Z, where in the dual, the shortest billiard orbit is a free orbit. So shortest billiard orbit is, I don't know, something like this. So here is the idea. We take the tangent lines to the boundary at these bouncing points. And we have this exterior triangle T out. And this green line must also be a billiard orbit in T out, because I chose the tangents in this way. So then alpha of T out is alpha of Kz. And the Kz is contained in T out. So now I can take the duals, which will reverse inclusions. So T out, the dual of T out with respect to the origin is contained in the dual of Kz, which is a shift of K. And when the dual of a triangle is a triangle, as we explained. So if I call this triangle T in, then this means that I have somewhere in the left picture this triangle. So and now I can look on this from another perspective. So I can say that T out is the dual of T in, and the billiard orbit in T in is a free orbit. So by the assumption of a reduction, and by assumption, we can conclude that the shortest billiard trajectory in T in Z is at least 8 over the diameter of T in, but this is just the alpha of Kz, and the diameter of the inner triangle is at most the diameter of K. So it can only increase this, decrease further this fraction. Okay, so if we know the claim for triangles, then we know it for arbitrary bodies. So it's enough to show that the claim holds for triangles. And we can make a further reduction, which also is also very simple, from arbitrary triangles to isosceles triangles. Second reduction. If a claim holds for isosceles triangles, in fact, I can insist that these triangles with apex angle at most pi over 3 then it holds for all triangles. And this is again quite simple. So if we have here an arbitrary triangle, so this is an arbitrary triangle T. So the diameter of T is its longest edge. So this is the diameter of T. So near the longest edge is the smallest angle. So let's suppose that this angle is the smaller. So this is smallest angle of T. So now we do the following procedure. We extend this edge until it will have the same length as the diameter. So now this is also a diameter of T, and we have here a new triangle T tilde. So now T is contained in T tilde, which is as isosceles triangles. And its apex angle is theta, which is at most pi over 3 because it is the smallest angle of T. And they have the same diameter. So now if we pass to the dual, so the dual of T tilde is contained inside the dual of T. So we have monotonicity of alpha. And if this is 8 over the diameter, then we are done. The diameter of T. Here we use the assumption. Okay, so this is the reduction to isosceles triangles. So what we are left with, and this is the part that you actually need to compute things. So we only need to show and by homogeneity of this quantity, I can restrict the diameter to have length 1 for simplicity. So if K is isosceles triangle with apex at most pi over 3 and diameter 1, and if the apex is the smallest angle, then the diameter are the legs of K. And if Z in K is a point for which alpha KZ is a free orbit, then we need to show that the alpha of KZ is at least 8. And this is done by computation, but I'll explain the main idea of right now. Do we need to take a break, something?
It depends on your decision. So
I think I have like 20 more minutes of stuff to talk about, so maybe we'll just continue.
fine with me.
Okay. So let's show this. So so I have an isosceles triangle K. Maybe I'm writing a new picture because this picture is quite big. I have an isosceles triangle K. And I want the dual to be a free orbit. In the dual to have a free orbit. So for that, I need that the dual will be an acute triangle. So like we explained in the beginning, we need that all of these points, if we connect the point Z to the three vertices, all of these angles will be obtuse. But this means that if we take a semicircle, which is based on every edge, then this point must be inside this semicircle, because on the circle itself, we have a right angle. So if we go inside, the angle will be obtuse. So this means that we need to draw these three semicircles based around the edges of K. And we need to consider only this domain. So the point Z must be inside this domain for KZ to have to be a acute triangle. So if we have this domain D, so for Z in D, KZ is acute. So now suppose we actually have this domain. Let's redraw this. So we have our three semicircles. Something like that. And we have our point Z. So now we draw a dual triangle. So it will be something like this. So let's also give names to everything. So these are ABC. And this will be A star, B star, C star. These are vertices of a dual triangle. So, so this is KZ. Now we want the shortest billiard orbit inside this dual. So as we explained, its length is equal to, if this is theta, and we take this altitude, yeah, so this altitude h, so by what we explained at the beginning, alpha of kz is twice this altitude times the sine of theta. Now we want to reconstruct it in terms of our original triangle. So this angle theta is the same angle in BZC, because if we connect these points here, and these angles are right angles, so in this quadrilateral, this must be pi minus theta. So we understand what the sine is. What about h? So h is a bit trickier. So instead of thinking about h itself, we draw a parallel line to B star C star that passes through A, and then h is the same length of this segment. Why is that useful? Because by definition of a dual, we can split it into two parts. So one part is this part, and by definition of a dual, this part is actually, its length is 1 over the length from A to Z. So if I draw A, if I connect A with C, by definition of a dual, this part is 1 over AZ. So H is 1 over AZ plus this part. And what is this part? So one can show from the, again, more or less of a definition of a dual, is that if we have this point D, then this length is 1 over ZD. So now we translated everything in terms of our original triangle, and we can forget about the dual. So now our function of k is the following function: connect z to one of the vertices, and it doesn't depend on the vertex because this formula does not depend on from which vertex you drop the altitude. So connect z to one of the vertices, and then compute this thing. So now we need to understand what this is. And this is more or less can be carried out explicitly. So it's a little bit, it's very tedious computations, but one can like completely characterize this. And the result of this computation, rather surprising. It doesn't look pretty at all, but the result is pretty. So the result is that if K is in isosceles triangles with a base angle beta, which is at least pi over 3, because the apex was at most pi over 3, and leg 1, then if kz is a free orbit, and alpha of kz is 2 times sine 2 beta over the product of z from the endpoints. So I think about z as a complex number, and ABC are the vertices. And so again, this is the triangle K, and I have my 3 circle arcs. So for all, these are ABC, and this is beta, and this is 1. So for all points here, this formula holds. And this is auspiciously elegant, and I have no idea why is it so pretty. But this is what you get after you compute this expression. And this expression is very nice because this is the absolute value of a complex polynomial. So just write it as 2 times sinus sine 2 beta over absolute value of a complex polynomial. And by the maximum principle, this thing cannot have local extreme points. So the minimal value of this function is attained when z is on the boundary. So minimum, so by maximum principle, the minimum of alpha kz when z is inside this domain D is attained for z in the boundary of D. And that's easy to analyze because at the boundary of D, this angle is just pi over 2. I'll go back to the previous thing. Then angle BZC at the boundary is always pi over 2. So for Z in the boundary, so well, if it's on this boundary. If it's on another arc of a boundary, then we just reuse this formula using another vertex. So instead of connecting it to A, we connect it to C, for example, and it will still be the same expression. It will be the sine of this angle times 1 over this length plus 1 over this length. So you can rephrase it to different vertices, and it will use the same argument. So if, for example, we are on the upper circle arc, then the angle is pi over 2, and then alpha of kz is 2 times 1 over az plus 1 over zd, but their length is fixed. I mean, their length is at most the length of AD, and the length of AD is at most 1, which is the diameter. So now, by more or less kind of harmonic arithmetic mean inequality, one can show that this is at most 8, because sum of AZ plus ZD is the length of AD, which is at most 1. So this shows, and then again, if Z is on this circle arc, then you repeat the same argument by connecting it to C. And you use the same formula. So this completes the proof that alpha of Kz is at least 8 over the diameter, and it is attained when Z is the midpoint of the diameter. So this completes the proof. What this means, so now corollaries of this, is that in R2, beta of K is 8 times alpha of K divided by the diameter of K. Because 8 over the diameter is the smallest value of alpha in the dual. Now for any K, the diameter of K is a billiard orbit, because the endpoints of a diameter, the supporting the lines are perpendicular to the diameter. So alpha K is at most twice the diameter. So we have here, this is at most 16, which is the value for the ball. And moreover, if beta K is 16, then it means that the diameter is twice alpha K, but the diameter is the maximal width. And the segment of minimal width of K is always a candidate to be a billiard orbit. So minimal width is a billiard orbit. So we see that the twice max width I'm sorry, but 2 is in the wrong place. Should be here. So twice the max width is at most twice the minimal width. So this means that the width is constant. And so this gives one implication. And if a width is constant, then it is known that in R2, then alpha K is a 2 orbit. And if it's a 2 orbit, then the shortest one is the minimal width. And then the minimal width is the same as the width is the same as the diameter. So in this fraction, we will just get 16. So then beta K is 16. And so this is about the global maximizers of the billiard product. Now, to finish, I just want to say a few words about the polygons. So one can ask, what is the maximum of beta K when K is a polygon with at most n vertices? So let's write beta n is the maximum of beta K, where K is a polygon with at most n vertices. And so the fact that so when we want to find these beta n, so one guess would be to try the regular polygons, and then one can compute everything. So for regular polygon, Rn is a regular polygon. So one can compute beta Rn, and the answer is that it's 12 when n is 3. And something trigonometric that I need to make sure I'm not getting wrong. 16 cosine pi over 2n when n is odd, and 16 cosine pi over n when n is even. Now, how does this sequence look like? So both sequences are monotone, but the odd sequence dominates the even sequence. So we have something that looks like this. So this is 3, 4, 5, 6, 7, 8, and so on. So this means that there is no way that the even with regular polygon with even number of vertices are the maximizers, because if I take, for example, the regular triangle. So, for example, in quadrilateral, you can take a regular triangle, chop it off near one of its edges, and then I get a quadrilateral. And this quantity beta k is continuous in k. So since I didn't change k much, I also didn't change the beta, the Billiard product by much. So then here I will get a quadrilateral, which is strictly better than a square. So the regular even polygons cannot be the maximizers. Now I do have a guess for what the optimal quadrilateral is, and I have some. I know to prove that it's better than some polygons, but not for general. But here is a regular, an optimal quadrilateral, which is better than a regular triangle. So the construction is the following: take an equilateral triangle. Yes. So this is an equilateral triangle. And extend its altitude until it will also have length 1. And now here I get Q, a quadrilateral. So I can write what this is. This is convex hull of plus minus half 0, 0 square root of 3 over 2, and 0 the square root of 3 over 2 minus 1. And the Billiard product of this quadrilateral is something like, I have it written, is 8 times square root of 3 cosine pi over 12. And this is more than 12. And now well, the question is whether this is indeed equal to beta 4. So this I don't know, but I didn't find any better quadrilateral yet. And they have proof in some cases and some numerical evidence to show for it. What happens in polygons with more vertices than where I'm less sure? I don't really have any guess for what the optimal is. But at least for quadrilateral, this type of rhombus is the best quadrilateral that I can find. So I think this is it.
Thank you very much. It was a very interesting talk. Just a moment.